Hello everyone who is watching this video, and let's get started. Okay, so first of all, I'll tell you what a general chemical process looks like. So basically you have raw materials which go into refinery and get out as fuels, or they go into further manufacture process and become base chemicals, and then become intermediates, and then finally become fine chemicals, which are then converted to consumer products. Okay, one important thing which I want, so basically you just see the amount and you can predict that where any compound will come. Some compounds can come in two or three places depending on the process. So one important thing which comes in questions and which you need to remember is any carbonyl will come into intermediates. That one thing you need to remember. Then there is some number crunching, and you have, if you have production of greater than 10,000 tons per annum, it is called a bulk chemical. And if it is less than 10,000 tons per annum, it is called a fine chemical or specialty chemical. Okay, with that then let's go and talk about few terms. First one is a steady state process. Steady state process, in a steady state process, the condition don't vary with time. So conditions don't vary with time. Okay, then you have a continuous process in which the inflow mass rate is equal to outflow mass rate. So there's, basically you can say, accumulation is equal to zero. Accumulation is how much of the mass is getting built up into the system. Okay, then third is batch. Basically in batch, you take a container, you store something, you do the reaction, and then after the reaction is done, you finally take it out. So when the reaction is happening, there's no input and there's no output. It's already stored inside. So that is batch. Then you have semi batch. In semi batch, there's input, there's output, but input is not equal to output, which means accumulation is not equal to zero. So that is semi batch. And then you have a term called transient state. Transient is just opposite of steady. So if the conditions vary with time, it is called transient state. Then you have recycle. I'll come to this in a moment. Recycle, and seventh is purge. Okay, so let's talk about these two terms. So basically, let's say you consider typical ammonia plant. It's good to have an idea. So yeah, so you have water and primarily from natural gas, coming in to a primary reformer, and then out of this you get H2, you get some CO, you get some CO2. See, H2 was the product we need for ammonia. Okay, and then you have a secondary reformer, and this you add some air. Air is basically O2 plus N2. You ignore the other gas, other things. Okay, then you have H2, you have N2, and O2 reacts with this. O2 reacts with this CO2, CO2, and H2 to give some H2O, some CO2, some CO is also remaining. Then you pass it through a water gas shift reaction, and then you get N2, you get H2, and you get CO2. This CO converts to CO2. Water gets somehow used up to get CO2, and then you pass it to an absorption tower in which you have K2CO3 coming in, KHCO3 going out, and then what comes out is N2 plus H2. Okay, so finally you have obtained your N2 plus H2. Now you pass this to a reactor. So this process I'm drawing again. So you have N2, you have H2, you pass it to a reactor. But suppose design stoichiometrically, so this is X and this is 3x molar. But the reactor does not convert it 100% at a time. Okay, so let's say you have X moles of N2 coming in, 3x moles of H2 coming in, and the conversion is not 100%. Let's say the conversion is 50%. So you will get only 50% of what you would have got, 2x, which is X moles of ammonia. Remaining 50% of nitrogen and hydrogen is still left. So you have X by 2 of N2 plus 3x by 2 of H2 still left. So here what you get out is N2, H2 and ammonia in these amounts. But if you just pass them out and separate ammonia and discard the other things, you are having a big loss, right? So what some intelligent people have done is they have separated it first. You have a condenser. Okay, you put a condenser. Ammonia gets liquid first, and N2 and H2 are still gases, so ammonia comes out, and remaining N2 and H2 you pass it back. Smart, right? You didn't lose anything. That's one thing. Okay, now yeah, let's remove this thing. Now let's say that only N2 and H2 are not. Although you remove most of the things, let's say that some argon has come into the system. Okay, some argon has come into the system. It's coming from here. It's coming from here. Where is the source? It's in air. Some argon is coming from air, let's say. Okay, so this argon has no place to get out of the system. It only keeps on going in, and only ammonia comes out. So argon keeps on getting cycled in this. So if you don't remove argon at some time, it will get accumulated in this, and at a time the reactor performance will go down because argon concentration will increase a lot. So what we can do is we can take out purge. So what this pulse does is basically whatever is coming out back here into H2 and some argon, you take out a part of it and let other part go inside and let other part go back. So this way some of the argon is reduced. This way you losing some into an H2, but then the argon concentration is regulated. So basically you optimize this thing so that you get the minimum purge, but still your reactor is not affected. That is one thing, and we'll discuss purge in detail in one of the videos. Okay. Then next thing, the most important thing is mass balance. So basically, mass balance is mass in equals to mass out because no mass is not created or destroyed. Assuming that we are not doing nuclear reaction where mass gets converted to energy. So yeah, mass in equals to mass out. That's the general thing for any boundary. For any boundary. So what is this boundary? Let's go back to this and make a boundary. So boundary does not cut a reactor, it just cuts the streams. So yeah, let's come here on itself. So if you draw a boundary like this, so this is one entry point, this is one exit point. So we are just saying that water mass is coming in from this point is leaving from this point. That is one thing. Now let's try with some other boundary. Mm, yeah, let's try with some other boundary. Let's consider this boundary. Okay, so this is one entry point, this is one exit point, and this is one exit point. We are just saying that mass which is coming in from here exits from here, mass out, and from here m out. So what is this? As you would have recognized, this is only for accumulation. Accumulation is equal to 0. Only then you can do mass balance. That is one thing. Okay. Now this is for the complete around the boundary. Now let's say you are going for only one component, right? So let's say we are talking only about N2. This was total mass in, and total mass out. Mass of H2, N2, ammonia, everything was there. Now we are talking only about one component. So in this, we can write the equation: coming in, mass coming in, minus going out, minus going out, minus reacted. So some nitrogen will get converted to NH3 ammonia. So we can say that nitrogen is reacted. It has gone down, plus generated is equal to zero. So basically, whatever mass is created and whatever is coming in is either reacted or it goes out. Again, this is only for accumulation is equal to zero. You can say for steady states, because in steady states concentration also not changing, so you can say accumulation is equal to zero. And again, this is for overall. Fine. Now let's say if for overall, let's talk in number of moles. So you cannot write number of moles in is equal to moles out, right? So let's say you have N2 plus 3H2 coming in, but you have only two ammonia going out in let's say 100% conversion. So this is 2 and this is 4. So unless and until it is not an equimolar reaction, you cannot write the overall balance for moles. You have to just write it as this is not equal to. It is like moles in minus moles out minus reacted plus generated is equal to 0. This is always valid. Okay. Now let's. This is mass in, mass out. Let's talk about rates. This was like total mass in some time. Now let's say in infinitesimal time. So you write dm by dt in small time dt. How much mass is coming? So let's write this as f t naught. F stands for rate. I don't know why they chose this convention, but yeah, F stands for rate, T stands for total, naught stands for which was original, minus FT. This stands for out. This is in, plus net generated. This is what? Generated minus reacted is equal to dNA by dt. So water moles are accumulating is equal to water is coming in minus water is going out plus water is generated minus water is reacted. So yeah, now let's number this term. Let's this one, this is two, this is three, and this is four. Now for continuous process, which is steady. See, continuous does not mean steady. Con- for example, when you're setting up an ammonia plant, in the beginning it will be an unsteady state because the things are setting up. But once it sets up, it will be steady throughout. So yeah, continuous does not always mean steady. Continuous is initially unsteady and then becomes steady. So I'm talking about continuous and steady. So which term will be zero? So when you are saying continuous and you are saying steady, which means accumulation is zero, and this terms represent accumulation. So term number four is going to be zero, right? Okay. Now let's consider batch. As we talk, batch does not have any input, does not have any output. So term one and term two are going to be zero. For continuous unsteady. So for continuous unsteady, you may have accumulation, you can have things like that. So here none. None of them is zero. For semi-batch. For semi-batch also, we cannot say that any one of them is zero, but we can say one thing for sure. We can say one is not equal to two, which means the input rate is not equal to output rate. That's all. Now, there's one more term. We are just talking about terms, normal terms in this. There's something called selectivity. So let's say A goes to B and B goes to C. This is a desired reaction. Desired. Let's say C plus D for a better understanding. And this is undesired reaction. Okay, so finally you are getting some constant, like let's say 100 moles were there. Out of that, 50 moles got converted and got 50 moles of B, and out of these 50, 25 moles went into 25 and 25. So yeah, this is 50. So basically, finally you have A ka 50 moles, B you have 25 moles, C you have 25, and D you have 25. Assuming all of them are equimolar reactions. Now we say that selectivity is defined as, this is one definition which is used in general, amount of desired product. So what is desired? B. So amount of desired product by amount of all side reaction desired by side product. So 25 plus 25, which is half. So yeah, selectivity is half. That is one thing. Now you can say what else? Conversion. Conversion is defined as the total amount of the reactant get out consumed. So let's say conversion of A. So how much is the conversion of A? What was the initial amount? 100. How much got reacted? 50. Rather say how much is remaining? 50. Yeah, 50 by 100. So this conversion is half. So basically initial minus remaining by initial. So this is the conversion. And then you have one more term called yield. Yield of B, let's say. Yield of B is basically what is the actual amount by what would have formed. So let's say hypothetical amount in absence of side reactions. So what is the actual amount of B forming here? 25. If there was no side reaction, if this reaction was not there, then what would have been the production of B? 50. So yeah, here yield of 50 is 50%. Yield of B is 50%. Okay, that's nice. Now there's something called law of mass action, which you would have studied, of course. Law of mass action. For the sake of completeness, I'm just writing it here. K equilibrium is concentration of C by concentration of D by concentration of A by concentration of B. In the reaction, A plus B goes to C plus D. And if the coefficient, all the coefficient are one, let's say coefficient is 2 somewhere, so you'll get square. Okay, those normal things. And then there's one thing that these terms concentrations can be written in terms of extent of reaction, how much on the reaction is completed. So let's say there was 100 moles, there was 100 moles, and let's say the reaction has gone to 50%. So you'll have 50, you'll have 50, you'll have 100, you'll have 50 here. So yeah, this 100 can be written in terms of extent of like 100 into 1 minus extent is concentration of B. 100 into extent into 2 because 2 is coefficient of C is concentration of C and things like that. So yeah, so this can be written in terms of extent. Okay, that is one thing. Then there's a concept of excess air. There are some small concepts which you'll get here and there, but yeah, you'll need them in the solving questions. Yeah, so excess air is this is the last point I'm touching for this, and then we'll go to the next video. Okay, so excess air, let's say you have hydrocarbon CnHl. Okay, so NnHl then we have some relation, but I'm just assuming. So excess air is basically you assume that right is correct. Assume that all the fuel, all the fuel is converted such that carbon gets converted to CO2 and hydrogen gets converted to H2. So basically, here you don't consider that what is the actual amount of, here you don't consider the actual conversion, neither this is not considered, neither you consider if C is going to CO, which is partial combustion, that is also ignored. You assume that C is going to CO2, H is going to H2O. In this, how much O2 is required? That is called theoretical air, theoretical air or theoretical oxygen. And what is excess air then? Excess air is, so generally we say that excess air is, let's say, 1.2 times the theoretical or stoichiometric air. So it's just 1.2. So uh, this is actual amount given. So let's say you're having 1 mole of CO, 1 mole of carbon, and you don't know, like, it's not concerned how much is converting, but you need to find out that how much is the theoretical air. So theoretical air will be 1 more O2, because 1 more carbon requires 1 more O2 to get converted to CO2. And then if it is given that excess air is 1.2 times theoretical, so you say that air provided is 1.2 mole. I know that this term is confusing. Excess does should mean difference, but here when you say excess is 1.2 times the theoretical, it means that the total air provided is 1.2 times the required one. Okay, then I'll stop the video here and let's meet in the next video.